Hello everyone, I'm Congcong Miao, a senior researcher in Tencent. Today, I and Yunming from Northwestern University will present our work, Tensor, Lightweight BGP Non-Stop Routing. We also collaborate with KOST and Tsinghua University.
Thanks, Congcong. I'll first present background and system design. Congcong will then present evaluation results and conclude the paper. So let's talk about BGP. As you all know, BGP is the sole protocol that stitches autonomous systems together, so it is crucial to the internet. Unfortunately, BGP might be interrupted due to either upgrades, which are predictable, or failures, which are unpredictable. Luckily, we can keep the BGP session alive from predictable disruptions by letting the peering router know the incoming changes beforehand. Such ability is called non-stop forwarding. And this mechanism has actually been standardized called graceful restart. On the other hand, we refer to the ability of keeping the BGP session alive during unpredictable disruptions as non-stop routing, or NSR in short. This is harder than NSF, and failing to do so will have a large impact on the running traffic. This is because during BGP failure, all packets on the social link will be rerouted or even dropped. This plot is the CDF average throughput for links between Tencent data center and peering ASs. We can see that the median throughput is 64 megabits per second, which means that 1 minute one link downtime will impact around 500 megabytes of traffic. And if we count the average throughput, a 1 minute one link downtime will impact over 200 gigabytes of traffic. Our goal here is to realize BGP NSR. But to do that, we need to come over 4 challenges. First, we want our solution to adapt to virtualized environment. This is because virtualizing the cloud gateway is the current trend for major cloud providers, but previous NSR solutions all rely on some kernel modification. This hinders the BGP NSR to adapt to virtualized environment. Next, we want to have a good performance. The throughput is mostly concerned here. Another issue of previous NSR solutions is that they all suffer from split brain problem. This means that both the primary and backup router mistakenly consider the others down, so both of them are trying to send packets out, which create a mess and disrupt the communication eventually. From perspective of distributed system, this is because there isn't enough components in the group. So primary and backup, that's 2, but 3 is needed for a single point failure recovery. Further, we want to have high system reliability. The existing solution usually involve modification of kernel, like introducing wrappers to the TCP/IP stack, also BGP program, device management, backup modules, and more. However, the more components involved, the less reliable the system is. We want to improve this. Okay, so we propose Tensor. At a high level, Tensor has 2 pieces of design. First, we'll have a kernel modification-free synchronous packet replication, which provides high system reliability and virtualization support. Next, we have lightweight virtualization architecture, which provides good performance and solves the split brain problem. Now, let's go into the design details. First, we want to understand why kernel is always involved in previous BGP replications. What if we just replicate the BGP messages at application layer? Let's look at this example. There are 2 gateway routers here. The peering router sends 3 packets to our router. And let's take a closer look at what happens to the packets at our router. So the packets will first arrive at the kernel and then be passed to the user space program. After that, the kernel will generate acknowledgement packets and send them back. This might happen at the same time when the BGP tries to replicate BGP level messages. So let's say at this time, our router returns all 3 acknowledgement packets, but it has only replicated 1 to the backup router. If our router goes down at this time, the backup router will take over the charge for the BGP session. But now the peering router has received the acknowledgement packets and hence has updated its standing buffer. As a result, packet 2 and 3 are missing and inconsistency occurred. So that's why kernel is needed for BGP replication. Okay, so let's see how we solve this. Our solution is simple. Specifically, we leverage the NetFilter hook to intercept outgoing acknowledgement packets. The NetFilter is a Linux kernel subsystem, so this does not involve modifying the kernel. And we delay these intercepted acknowledgement packets until we confirm that the corresponding messages have been properly replicated out database. As a result, Tensor avoids kernel modification and provides virtualization support. It further minimizes the involved components. Right now, we only need to modify the BGP program. So the system reliability is substantially improved. Of course, this solution also has drawback. That is, the performance will be impacted. But this problem also applies to other NSR solutions as well. Let's study this. The axis of this plot is acknowledgement delay, and the y-axis is the maximum throughput. We can see that throughput decreases as the acknowledgement delay increases. However, the throughput did not decrease from the very beginning. There's a threshold. The throughput is not impacted before it reaches the throughput threshold. Now, if we can limit the acknowledgement delay within the threshold, then we can minimize the performance degradation. And by doing that, we are actually limiting the replication size. So how do we do that? We propose to virtualize the gateway router first, and more importantly, we split the BGP tables into multiple containers, so each container is only responsible for a small portion of routing updates. More details about how we split the BGP table, please refer to our paper. By doing this, each container only needs to replicate a few packets each time, so the performance degradation from the delay acknowledgement is minimized. Additionally, this also minimizes the impact of a failure. One more thing to mention is that on the right-hand side of the figure, we further have agent server. We use agent server to keep BFD alive. BFD is a network protocol that is used to detect link failures, and it is also used together with BGP. By doing this, we don't need a backup container to replicate everything all the time. Instead, we can allow cold start or warm start of backup containers, which saves resources. We further implement various inter-component communications. This helps Tensor to solve the split brain problem because now there are many more components. We have controller, primary container, agent server, and optionally backup container and other containers. This is more than enough for single point failures that we're trying to tackle.
Thanks, Yunming. I will now take over to present the evaluation results. First, let's take a look at whether and how NSR will impact the BGP performance. In the figure on the right-hand side, the x-axis is the number of routing updates and the y-axis is the time to process them when receiving from peers. The blue line is Tensor with NSR and the others are BGP implementations without NSR. Overall, Tensor costs some extra time to process because of delayed ACKs. But we can see that on the normal workload, the maximum additional processing time is less than 100 milliseconds. This is accessible to our production network, so Tensor satisfies our performance requirements when receiving routing updates. Next, this plot shows the performance when sending to other peers. We see that the blue line, which is the Tensor, is basically overlapping with other lines. This means that Tensor achieves nearly the same performance as other BGP implementations when sending out routing updates. Next, we'll look at the operational benefits. Let's first take a look at the failure recovery. For other software BGP implementations, they need to take tens of seconds or even minutes to recover from a BGP failure. Depending on the failure type, for more detailed results, please refer to our paper. And such recovery is offline, meaning that the peer router will acknowledge the downtime on our side, and the ongoing traffic will be impacted. In other words, the NSR is not enabled in this case. On the other hand, Tensor and NSR-enabled router only take a few seconds to recover any failures, and such recovery is online, meaning that the other side does not acknowledge the downtime and ongoing traffic is not impacted. So Tensor speeds up the failure handling by 1 or 2 orders of magnitude compared to other software BGP implementations and achieves the same service level agreements with NSR-enabled routers. Next, we take a look at the operational costs. Tensor is developed based on the existing software BGP implementations. So we mainly compare against the NSR-enabled routers. We see that Tensor is much easier to realize, taking less than a year to complete, whereas NSR-enabled router may take a few years. Tensor also bears less deployment and maintenance cost. Overall, Tensor reduces the development, deployment, and maintenance cost by factor of 5 to 20. Compared to NSR-enabled routers. In conclusion, We present Tensor, a virtualized BGP system that supports NSR capability. Tensor incorporates a kernel modification-free packet replication design and lightweight virtualized architecture for improved performance. Tensor bears minimal to acceptable performance overheads compared to popular open-source BGP implementations while providing significant benefits in failure recovery. Tensor significantly reduces the development, deployment, and maintenance costs while retaining the same service level agreements as NSR-enabled routers.